In this video, I'm going to talk about thermal energy transfers. Specifically, I'm going to talk about conduction, convection, and radiation. Take a moment and read the success criteria I plan to cover during this video. Okay, so just to point out for these slides, we're going to talk about conduction, convection, radiation. But it really should be review at this point for you. So what I'm going to do is I'm going to focus on some experiments that will help us figure out more about these types of heat transfer. So for conduction, we're talking about the flow of thermal energy via contact. So you can see here, I've got an experiment and I have these paper clips being attached here by Vaseline, or sometimes we could talk about them being attached by wax. And if I put a Bunsen burner here at the end, as this rod heats up, the heat will travel along via conduction from one end to the other. And we'll be able to see how long it takes for each piece of wax to melt, and then the paper clips will fall. We can talk about the conduction of the metal in general. This says copper rod, and we know metals are good conductors of heat. And this is because they contain free electrons, which also help to pass on the heat via conduction. When they rapidly vibrate as they're being heated, they will help move energy from the hot end to the cold end. That means heat will travel more quickly than with other materials without those free electrons. You can see here I have 4 different kinds of metals, and again we've got a place where we could put some wax. If we want to have a paper clip we could attach, or we could just see when the wax would melt in these little divots. Now, if we want to talk about the rate of conduction, we can be a little bit more sophisticated. So here's an equation that we have in our data booklet. So change in Q over change in time. Well, we know Q stands for heat. So this would be standing for the rate of which heat was transferred. Because remember, anything divided by T is per time, or the rate of. I've got a constant, and that will depend on what material I'm using. Something like a metal that's a good conductor of heat will have a value typically in the 400s or so of joules per degrees per distance, where something like air that's an insulator is going to have a very low number, below 1. A will be the surface area, so if I'm using this, if this was a window, for example, this would be the thickness of the window, a few millimeters. But the area might be like 1 meter times 1.5 meters in order to calculate the surface area. So it would be sticking out of my computer from right here. Change in temperature. The bigger the difference in temperature, the faster the heat will travel through your window. And then delta X being the thickness of the actual glass. Now if we start to talk about convection, now we're starting talking about fluids rather than solids that we were in conduction. In fluids, the particles can actually move from place to place rather than just vibrate in position. Heat energy is still going to be transferred from hot places to cold places, but now remember, liquids can expand not because the particles get larger, but rather as they're heated, the particles move faster, and then they move farther apart. As a result of this, they take up more volume for the same amount of mass. This makes them less dense, and then the less dense material will rise. So I've got a video here, and you can go link to see how it happens. This started off with cold water on the bottom and hot water on the top, and over time it just has a little bit of mixing right here. But in this case, when it had the hot water on the bottom and the cold water on the top, this hot water being less dense is going to rise to the top bottle, and the cold water will sink. And you can see here how much more mixing we've had between the cold and hot water. Radiation. Now, this is thermal radiation we're talking about, not nuclear. So we're talking about electromagnetic waves, specifically those in the infrared region. Anything that has a temperature will actually give off these EM waves. And you can see here I've got a few different examples. In this case, this Leslie cube, what you do is you can fill this up with hot water. And then you can measure the shiny black side, the temperature, the matte white, matte black, or shiny silver. And what you can do is then you can see which one gives off the most temperature. And this is due to giving off infrared radiation. Similarly here, if I put this into the sunlight, instead of emitting infrared radiation like in this one, we could be measuring the things that absorb infrared. And what usually happens in all these cases is that the surface that's a good radiator of heat is also a good absorber of heat. So in this cases, it would be the black surfaces that are rough or matte. That's why in the summer, the black cars will get a hotter surface than a poor radiator. It's also why many of the houses in the Mediterranean are going to be painted white. They're going to reflect the infrared light landing on it rather than absorbing it, keeping the house cooler. One last thing to point out is, since this is EM waves, we don't have to have a medium, which is a really good thing because I kind of like the heat that's coming from the sun. Okay, so let's do a couple of examples. First of all, I have a double-walled glass vacuum flask. It's a big mouthful, and most of the thermoses that you use are actually of this type. At least the ones that are a little bit more expensive, but also keep things either very, very hot for a long time or very cold. So what happens is in between these two sides here, in where my cursor is showing you, that will be the vacuum. So without particles, that means I'm not going to be able to have conduction or convection. So the first part says why the rate of loss of thermal energy through the walls of the flask by conduction is very low. Well, without particles, I can't have heat transfer via contact, therefore no conduction. Why the rate of loss of thermal energy through the walls is very low? Well, that has to do with this silvered surface. Remember, this will reflect the infrared radiation, therefore either bouncing back in or bouncing back out, but not letting it go from one way to the other. Suggest with reasons what must be added to the flask shown in the figure in order to keep it hot. Well, look right here. What we're missing is a lid. What would the lid do? Well, it was going to stop heat leaving via convection. And for another example, state the main method of heat transfer by which energy from the fire reaches the person sitting nearby. Now, I would suggest that we have two different things going on. If I'm talking about the hands, that would be convection. The hot air is going to rise and touch his hand. And then as it's touching his hand, we'll have conduction. But if we were talking about his feet, now this is beside it. Convection is going to cause it to rise upwards, so his feet must be getting hot because of radiation. And as our bodies absorb the radiation, we will feel it as being hot. I'm just going to put in brackets the infrared. Part B. A spark jumps out of the fire and lands on his hand. Well, that's going to have to now be conduction. That's due to touch. Well, I hope those examples of the experiments and the applications to real life has helped you out. Please read the success criteria one more time, and hopefully you can say yes to these 3 things.